Okay. Carl Sagan, The Demon-Haunted World, Chapter 19, No Such Thing as a Dumb Question. Quote, so we keep asking over and over until a handful of earth stops our mouths. But is that an answer? End quote. Heinrich Heine, Lazarus, 1854. In East Africa, and the records of the rocks dating back to about 2 million years ago, you can find a sequence of worked tools that our ancestors designed and executed. Their lives depended on making and using these tools. This was, of course, early Stone Age technology. Over time, specially fashioned stones were used for stabbing, chipping, flaking, cutting, carving. Although there are many ways of making stone tools, what is remarkable is that in a given site for enormous periods of time, the tools were made in the same way, which means that there must have been educational institutions hundreds of thousands of years ago, even if it was mainly an apprenticeship system. While it's easy to exaggerate the similarities, it's also easy to imagine the equivalent of professors and students in loincloths, laboratory courses, examinations, failing grades, graduation ceremonies, and postgraduate education. When the training is unchanged for immense periods of time, traditions are passed on intact to the next generation. But when what needs to be learned changes quickly, especially in the course of a single generation, it becomes much harder to know what to teach and how to teach it. Then, students complain about relevance. Respect for their elders diminishes. Teachers despair at how educational standards have deteriorated and how lackadaisical students have become. In a world in transition, students and teachers both need to teach themselves one essential skill: learning how to learn. Except for children who don't know enough not to ask the important questions, few of us spend much time wondering why nature is the way it is, where the cosmos came from, or whether it was always here. If time will one day flow backward and effects precede causes, or whether there are ultimate limits to what humans can know. There are even children, and I have met some of them, who want to know what a black hole looks like. What is the smallest piece of matter? Why we remember the past and not the future, and why there is a universe. Every now and then, I'm lucky enough to teach a kindergarten or first grade class. Many of these children are natural-born scientists, although heavy on the wonder side and light on the skepticism. They're curious, intellectually vigorous, provocative and insightful questions bubble out of them. They exhibit enormous enthusiasm. I'm asked follow-up questions. They've never heard of the notion of a dumb question. But when I talk to high school seniors, I find something different. They memorize facts. By and large, though, the joy of discovery, the life behind those facts, has gone out of them. They've lost much of the wonder and gained very little skepticism. They're worried about asking dumb questions. They're willing to accept inadequate answers. They don't pose follow-up questions. The room is awash with sidelong glances to judge, second by second, the approval of their peers. They come to class with their questions written out on pieces of paper, which they surreptitiously examine, waiting their turn and oblivious of whatever discussion their peers are at this moment engaged in. Something has happened between 1st and 12th grade, and it's not just puberty. I'd guess that it's partly peer pressure not to excel, except in sports. Partly that the society teaches short-term gratification, partly the impression that science or mathematics won't buy you a sports car, partly that so little is expected of students, and partly that there are few rewards or role models for intelligent discussion of science and technology, or even for learning for its own sake. Those few who remain interested are vilified as nerds or geeks or grinds. But there's something else. I find many adults are put off when young children pose scientific questions. Why is the moon round? The children ask. Why is grass green? What is a dream? How deep can you dig a hole? When is the world's birthday? Why do we have toes? Too many teachers and parents answer with irritation or ridicule or quickly move on to something else. What did you expect the moon to be? Square? Children soon recognize that somehow this kind of question annoys the grown-ups. A few more experiences like it, and another child has been lost to science. Why adults should pretend to omniscience before 6-year-olds, I can't for the life of me understand. What's wrong with admitting that we don't know something? Is our self-esteem so fragile? What's more, many of these questions go to deep issues in science, a few of which are not yet fully resolved. Why the moon is round has to do with the fact that gravity is a central force pulling towards the middle of any world, and with how strong rocks are. Grass is green because of the pigment chlorophyll. Of course, we've all had that drummed into us by high school, but why do plants have chlorophyll? It seems foolish since the sun puts out its peak energy in the yellow and green part of the spectrum. Why should plants all over the world reject sunlight in its most abundant wavelengths? Maybe it's a frozen accident from the ancient history of life on Earth. But there's something we still don't understand about why grass is green. There are many better responses than making a child feel that asking deep questions constitutes a social blunder. If we have an idea of the answer, we can try to explain. Even an incomplete attempt constitutes a reassurance and encouragement. If we have no idea of the answer, we can go to the encyclopedia. If we don't have an encyclopedia, we can take the child to a library. Or we might say, I don't know the answer. Maybe no one knows. Maybe when you grow up, you'll be the first person to find out. There are naive questions, tedious questions, ill-phrased questions, questions put after inadequate self-criticism, but every question is a cry to understand the world. Footnote, I'm excluding the fusillade of whys that 2-year-olds sometimes pelt their parents with, perhaps in an effort to control adult behavior. End footnote. There is no such thing as a dumb question. Bright, curious children are a national and world resource. They need to be cared for, cherished, and encouraged. But mere encouragement isn't enough. We must also give them the essential tools to think with. It's official, reads one newspaper headline. We stink in science. In tests of average 17-year-olds in many world religions, the U.S. ranked dead last in algebra. On identical tests, the U.S. kids averaged 43% and their Japanese counterparts 78%. In my book, 78% is pretty good. It corresponds to a C+, or maybe even a B-. 43% is an F. In a chemistry test, students in only 2 of 13 nations did worse than the U.S. Britain, Singapore, and Hong Kong were so high they were almost off scale. And 25% of Canadian 18-year-olds knew just as much chemistry as a select 1% of American high school seniors in their second chemistry course, and most of them in advanced placement programs. The best of 20 fifth grade classrooms in Minneapolis was outpaced by every one of 20 classrooms in Sendai, Japan, and 19 out of 20 in Taipei, Taiwan. South Korean students were far ahead of American students in all aspects of mathematics and science, and 13-year-olds in British Columbia, in Western Canada, outpaced their U.S. counterparts across the board. In some areas, they did better than the Koreans. Of the U.S. kids, 22% say they dislike school. Only 8% of the Koreans do. Yet 2/3 of the Americans, but only 1/4 of the Koreans, say they are good at mathematics. Such dismal trends for average students in the United States are occasionally offset by the performance of outstanding students. In 1994, American students at the International Mathematical Olympiad in Hong Kong achieved an unprecedented perfect score, defeating 360 other students from 68 nations in algebra, geometry, and number theory. One of them, 17-year-old Jeremy Bem, commented, "Math problems are logic puzzles. There's no routine. It's all very creative and artistic. But here I'm concerned not with producing a new generation of first-rate scientists and mathematicians, but a scientifically literate public." 63% of American adults are unaware that the last dinosaur died before the first human arose. 75% do not know that antibiotics kill bacteria, but not viruses. 57% do not know that electrons are smaller than atoms. Polls show that something like half of American adults do not know that the Earth goes around the sun and takes a year to do it. I can find in my undergraduate classes at Cornell University bright students who do not know that the stars rise and set at night, or even that the sun is a star. Because of science fiction, the educational system, NASA, and the role that science plays in society, Americans have much more exposure to the Copernican insight than does the average human. A 1993 poll by the China Association of Science and Technology shows that, as in America, no more than half the people in China know that the Earth revolves around the sun once a year. It may very well be, then, that more than 4.5 centuries after Copernicus, most people on Earth still think, in their heart of hearts, that our planet sits immobile at the center of the universe and that we are profoundly special. These are typical questions in scientific literacy. The results are appalling. But what do they measure? The memorization of authoritative pronouncements. What they should be asking is how we know that antibiotics discriminate between microbes, that electrons are smaller than atoms, that the sun is a star which the Earth orbits once a year. Such questions are a much truer measure of public understanding of science, and the results of such tests would doubtless be more disheartening still. If you accept the literal truth of every word in the Bible, then the earth must be flat. The same is true for the Quran. Pronouncing the earth round then means you're an atheist. In 1993, the supreme religious authority of Saudi Arabia, Sheikh Abdelaziz ibn Baz, issued an edict or fatwa declaring that the world is flat. Anyone of the round persuasion does not believe in God and should be punished. Among many ironies, the lucid evidence that the earth is a sphere, accumulated by the 2nd century Greco-Egyptian astronomer Claudius Ptolemaeus, was transmitted to the West by astronomers who were Muslim and Arab. In the 9th century, they named Ptolemy's book in which the sphericity of the earth is demonstrated, the Alchemist, the greatest. I meet many people offended by evolution who passionately prefer to be the personal handicraft of God than to arise by blind physical and chemical forces over aeons from slime. They also tend to be less than assiduous in exposing themselves to the evidence. Evidence has little to do with it. What they wish to be true, they believe is true. Only 9% of Americans accept the central finding of modern biology, that human beings and all the other species have slowly evolved by natural processes from a succession of more ancient beings with no divine intervention needed along the way. When asked merely if they accept evolution, 45% of Americans say yes. The figure is 70% in China. When the movie Jurassic Park was shown in Israel, it was condemned by some Orthodox rabbis because it accepted evolution and because it taught that dinosaurs lived 100 million years ago, when, As is plainly stated at every Rosh Hashanah and every Jewish wedding ceremony, the universe is less than 6,000 years old. The clearest evidence of our evolution can be found in our genes. But evolution is still being fought, ironically, by those whose own DNA proclaims it. In the schools, in the courts, in textbook publishing houses, and on the question of just how much pain we can inflict on other animals without crossing some ethical threshold. During the Great Depression, teachers enjoyed job security, good salaries, respectability. Teaching was an admired profession, partly because learning was widely recognized as the road out of poverty. Little of that is true today. And so science and other teaching is too often incompetently or uninspiringly done. Its practitioners, astonishingly, having little or no training in their subjects, impatient with the method, and in a hurry to get to the findings of science, and sometimes themselves unable to distinguish science from pseudoscience. Those who do have the training often get higher paying jobs elsewhere. Children need hands-on experience with the experimental method rather than just reading about science in a book. We can be told about oxidation of wax as the explanation of the candle flame, but we have a much more vivid sense of what's going on if we witness the candle burning briefly in a bell jar until the carbon dioxide produced by the burning surrounds the wick, blocks access to oxygen, and the flame flickers and dies. We can be taught about mitochondria in cells, how they mediate the oxidation of food like the flame burning the wax, but it's another thing altogether to see them under the microscope. We may be told that oxygen is necessary for the life of some organisms and not others. But we begin to really understand when we test the proposition in a bell jar fully depleted of oxygen. What does oxygen do for us? Why do we die without it? Where does the oxygen in the air come from? How secure is the supply? Experiment and the scientific method can be taught in many matters other than science. Daniel Kunitz is a friend of mine from college. He spent his life as an innovative junior and senior high school social sciences teacher. Want the students to understand the Constitution of the United States? You could have them read it, article by article, and then discuss it in class. But sadly, this will put most of them to sleep. Or you could try the Kunitz method. You forbid the students to read the Constitution. Instead, you assign them, 2 for each state, to attend a constitutional convention. You brief each of the 13 teams in detail on the particular interests of their state and region. The South Carolina delegation, say, would be told of the primacy of cotton, the necessity and morality of the slave trade, the danger posed by the industrial North, and so on. The 13 delegations assemble, and with a little faculty guidance, but mainly on their own, over some weeks, write a constitution. Then they read the real Constitution. The students have reserved war-making powers to the president. The delegates of 1787 assigned them to Congress. Why? The students have freed the slaves. The original Constitution Convention did not. Why? This takes more preparation by the teachers and more work by the students, but the experience is unforgettable. It's hard not to think that the nations of the earth would be in better shape if every citizen went through a comparable experience. We need more money for teachers' training and salaries and for laboratories. But all across America, school bond issues are regularly voted down. No one suggests that property taxes be used to provide for the military budget, or for agriculture subsidies, or for cleaning up toxic wastes. Why just education? Why not support it from general taxes on the local and state levels? What about a special education tax for those industries with special needs for technically trained workers? American school children don't do enough school work. There are 180 days in the standard school year in the United States, as compared with 220 in South Korea, about 230 in Germany, and 243 in Japan. Children in some of these countries go to school on Saturday. The average American high school student spends 3.5 hours a week on homework. The total time devoted to studies in and out of the classroom is about 20 hours a week. Japanese 5th graders average 33 hours a week in Japan, with half the population of the United States, produces twice as many scientists and engineers with advanced degrees every year. During 4 years of high school, American students spend less than 1,500 hours on such subjects as mathematics, science, and history. Japanese, French, and German students spend more than twice as much time. A 1994 report commissioned by the U.S. Department of Education notes, quote, "The traditional school day must now fit in a whole set of requirements for what has been called the new work of the schools. Education about personal safety, consumer affairs, AIDS, conservation and energy, family life, and driver's training." End quote. So because of the deficiencies of the society and the inadequacies of education in the home, only about 3 hours a day are spent in high school on the core academic subjects. There's a widely held perception that science is too hard for ordinary people. We can see this reflected in the statistic that only around 10% of American high school students ever opt for a course in physics. What makes science suddenly too hard? Why isn't it too hard for the citizens of all those other countries that are outperforming the United States? What has happened to the American genius for science, technical innovation, and hard work? Americans once took enormous pride in their inventors who pioneered the telegraph, telephone, electric light, phonograph, automobile, and airplane. Except for computers, all that seems a thing of the past. Where did all that Yankee ingenuity go? Most American children aren't stupid. Part of the reason they don't study hard is that they receive very few tangible benefits when they do. Competency, that is, actually knowing the stuff, in verbal skills, mathematics, science, and history these days doesn't increase earnings for average young men in their first 8 years out of high school, many of whom take service jobs rather than work industrial ones. In the productive sectors of the economy, though, the story is often different. There are furniture factories, for example, in danger of going out of business, not because there are no customers, but because so few entry-level workers can do simple arithmetic. A major electronics company reports that 80% of its job applicants can't pass a 5th grade mathematics test. The United States already is losing some $40 billion a year, mainly in lost productivity and the cost of remedial education, because workers, to too great a degree, can't read, write, count, or think. In a survey by the U.S. National Science Board of 139 high-technology companies in the United States, the chief causes of the research and development decline attributable to national policy were 1. Lack of a long-term strategy for dealing with the problem, 2. Too little attention paid to the training of future scientists and engineers, 3. Too much investment in defense and not enough in civilian research and development, and 4. Too little attention paid to pre-college education. Ignorance feeds on ignorance. Science phobia is contagious. Those in America with the most favorable view of science tend to be young, well-to-do, college-educated white males. But 3/4 of new American workers in the next decade will be women, non-whites, and immigrants, failing to rouse their enthusiasm, to say nothing of discriminating against them, isn't only unjust, it's also stupid and self-defeating. It deprives the economy of desperately needed skilled workers. African American and Hispanic students are doing significantly better in standardized science tests now than in the late 1960s, but they're the only ones who are. The average math gap between white and black U.S. high school graduates is still huge, 2 to 3 grade levels, but the gap between white U.S. high school graduates and those, say, in Japan, Canada, Great Britain, or Finland is more than twice as large, with the US students behind. If you're poorly motivated and poorly educated, you won't know much. No mystery there. Suburban African Americans with college-educated parents do just as well in college as suburban whites with college-educated parents. According to some statistics, enrolling a poor child in a Head Start program doubles his or her chances to be employed later in life. One who completes an Upward Bound program is 4 times as likely to get a college education. If we're serious, we know what to do. What about college and university? Those are obvious steps to take. Improve status based on teaching success, and promotions of teachers based on the performance of their students in standardized double-blind tests, salaries for teachers that approach what they could get in industry, more scholarships, fellowships, and laboratory equipment, imaginative, inspiring curricula and textbooks in which the leading faculty members play a major role, laboratory courses required of everyone to graduate, and special attention paid to those traditionally steered away from science. We should also encourage the best academic scientists to spend more time on public education, textbooks, lectures, newspaper and magazine articles, TV appearances, and a mandatory freshman or sophomore course in skeptical thinking and the methods of science might be worth trying. The mystic William Blake stared at the sun and saw angels there, while others, more worldly, perceived only an object of about the size and color of a golden guinea. Did Blake really see angels in the sun, or was it some perceptual or cognitive error? I know of no photograph of the sun that shows anything of the sort. Did Blake see what the camera and the telescope cannot? Or does the explanation lie much more inside Blake's head than outside? And is it not the truth of the sun's nature as revealed by modern science far more wonderful? No mere angels or gold coin, but an enormous sphere into which 1,000,000 Earths could be packed, in the core of which the hidden nuclei of atoms are being jammed together, hydrogen transfigured into helium, the energy latent in hydrogen for billions of years released, the Earth and other planets warmed and lit thereby, and the same process repeated 400 billion times elsewhere in the Milky Way galaxy. The blueprints, detailed instructions, and job orders for building you from scratch would fill about 1,000 encyclopedia volumes if written out in English. Yet every cell in your body has a set of these encyclopedias. A quasar is so far away that the light we see from it began its intergalactic voyage before the Earth was formed. Every person on Earth is descended from the same not quite human ancestors in East Africa a few million years ago, making us all cousins. Whenever I think about any of these discoveries, I feel a tingle of exhilaration. My heart races. I can't help it. Science is an astonishment and a delight. Every time a spacecraft flies by a new world, I find myself amazed. Planetary scientists ask themselves, "Oh, is that the way it is? Why didn't we think of that?" But nature is always more subtle, more intricate, more elegant than what we are able to imagine. Given our manifest human limitations, what is surprising is that we have been able to penetrate so far into the secrets of nature. Nearly every scientist has experienced, in a moment of discovery or sudden understanding, a reverential astonishment. Science, pure science, science not for any practical application, but for its own sake, is a deeply emotional matter for those who practice it, as well as for those non-scientists who every now and then dip in to see what's been discovered lately. And, as in a detective story, it's a joy to frame key questions, to work through alternative explanations, and maybe even to advance the process of scientific discovery. Consider these examples, some very simple, some not, chosen more or less at random. It's a long sequence of bullet points. Could there be an undiscovered integer between 6 and 7? Could there be an undiscovered chemical element between atomic number 6, which is carbon, and atomic number 7, which is nitrogen? Yes, the new preservative causes cancer in rats, but what if you have to give it to a person who weighs much more than a rat, a pound a day of the stuff to induce cancer? In that case, maybe the new preservative isn't all that dangerous. Might the benefit of having food preserved for long periods outweigh the small additional risk of cancer? Who decides? What data do they need to make a prudent decision? In a 3.8 billion-year-old rock, you find a ratio of carbon isotopes typical of living things today, and different from inorganic sediments. Do you deduce abundant life on Earth 3.8 billion years ago? Or could the chemical remains of more modern organisms have infiltrated into the rock? Or is there a way for isotopes to separate in the rock apart from biological processes? Sensitive measurements of electrical currents in the human brain show that when certain memories or mental processes occur, particular regions of the brain go into action. Can our thoughts, memories, and passions all be generated by particular circuitry of the brain neurons? Might it ever be possible to simulate such circuitry in a robot? Would it ever be feasible to insert new circuits or alter old ones in the brain in such a way as to change opinions, memories, emotions, logical deductions? Is tampering wildly dangerous? Your theory of the origin of the solar system predicts many flat disks of gas and dust all over the Milky Way galaxy. You look through the telescope and find flat disks everywhere. You happily conclude that your theory is confirmed, but it turns out the disks you cited were spiral galaxies far beyond the Milky Way and much too big to be nascent solar systems. Should you abandon your theory? Or should you look for a different kind of disk? Or is this just an expression of your unwillingness to abandon a discredited hypothesis? A growing cancer sends out an all-points bulletin to the cells lining adjacent blood vessels. We need blood, the message says. The endothelial cells obligingly build blood vessel bridges to supply the cancer cells with blood. How does this come about? Can the message be intercepted or canceled? You mix violet, blue, green, yellow, orange, and red paints and make a murky brown. Then you mix light of the same colors and you get white. What's going on? In the genes of humans and many other animals, there are long, repetitive sequences of hereditary information called nonsense. Some of these sequences cause genetic diseases. Could it be that segments of the DNA are rogue nucleic acids, reproducing on their own, in business for themselves, disdaining the well-being of the organism they inhabit? Many animals behave strangely just before an earthquake. What do they know that seismologists don't? The ancient Aztec and the ancient Greek words for God are nearly the same. Is this evidence of some contact or commonality between the two civilizations? Or should we expect occasional such coincidences between two wholly unrelated languages merely by chance? Or could, as Plato thought in the Cratylus, certain words be built into us from birth? The second law of thermodynamics states that in the universe as a whole, disorder increases as time goes on. Of course, locally worlds and life and intelligence can emerge at the cost of a decrease in order elsewhere in the universe. But if we live in a universe in which the present Big Bang expansion will slow, stop, and be replaced by a contraction, might the second law then be reversed? Can effects precede causes? The human body uses concentrated hydrochloric acid in the stomach to dissolve food and aid digestion. Why doesn't the hydrochloric acid dissolve the stomach? The oldest stars seem to be, at the time I'm writing, older than the universe. Like the claim that an acquaintance has children older than she is, you don't have to know very much to recognize that someone has made a mistake. Who? The technology now exists to move individual atoms around, so long and complex messages can be written on an ultra-microscopic scale. It is also possible to make machines the size of molecules. Rudimentary examples of both of these nanotechnologies are now well demonstrated. Where does this take us in another few decades? In several different laboratories, complex molecules have been found that, under suitable conditions, make copies of themselves in the test tube. Some of these molecules are, like DNA and RNA, built out of nucleotides. Others are not. Some use enzymes to hasten the pace of the chemistry. Others do not. Sometimes there is a mistake in copying from that point forward. The mistake is copied in successive generations of molecules. Thus, there get to be slightly different species of self-replicating molecules, some of which reproduce faster or more efficiently than others. These preferentially thrive. As time goes on, the molecules in the test tube become more and more efficient. We are beginning to witness the evolution of molecules. How much insight does this provide about the origin of life? Why is ordinary ice white, but pure glacial ice blue? Life has been found miles below the surface of the earth. How deep does it go? The Dogon people in the Republic of Mali are said by a French anthropologist to have a legend that the star Sirius has an extremely dense companion star. Sirius in fact does have such a companion, although it requires fairly sophisticated astronomy to detect it. So, 1. Did the Dogon people descend from a forgotten civilization that had large optical telescopes and theoretical astrophysics? Or 2. Were they instructed by extraterrestrials? Or 3. Did the Dogon hear about the white dwarf companion of Sirius from a visiting European? Or 4. Was the French anthropologist mistaken, and the Dogon in fact never had such a legend? Why should it be hard for scientists to get science across? Some scientists, including some very good ones, tell me they'd love to popularize, but feel they lack talent in this area. Knowing and explaining, they say, are not the same thing. What's the secret? There's only one, I think. Don't talk to the general audience as you would talk to your scientific colleagues. There are terms that convey your meaning instantly and accurately to fellow experts. You may parse these phrases every day in your professional work, but they do no more than mystify an audience of non-specialists. Use the simplest possible language. Above all, remember how it was before you yourself grasped whatever it is you're explaining. Remember the misunderstandings that you almost fell into, and note them explicitly. Keep firmly in mind that there was a time when you didn't understand any of this either. Recapitulate the first steps that led you from ignorance to knowledge. Never forget that native intelligence is widely distributed in our species. Indeed, it is the secret of our success. The effort involved is slight, the benefits great. Among the potential pitfalls are oversimplification, the need to be sparing with qualifications and quantifications, inadequate credit given to the many scientists involved, and insufficient distinctions drawn between helpful analogy and reality. Doubtless, compromises must be made. The more you make such presentations, the clearer it is which approaches work and which do not. There is a natural selection of metaphors, images, analogies, anecdotes. After a while, you find that you can get almost anywhere you want to go, walking on consumer-tested stepping stones. You can then fine-tune your presentations for the needs of a given audience. Like some editors and television producers, some scientists believe the public is too ignorant or too stupid to understand science, that the enterprise of popularization is fundamentally a lost cause, or even that it's tantamount to fraternization, if not outright cohabitation with the enemy. Among the many criticisms that could be made of this judgment, along with its insufferable arrogance and its neglect of a host of examples of highly successful science popularizations, is that it is self-confirming, and also for the scientists involved, self-defeating. Large-scale government support for science is fairly new, dating back only to World War II, although patronage of a few scientists by the rich and powerful is much older. With the end of the Cold War, the national defense trump card that provided support for all sorts of fundamental science became virtually unplayable. Only partly for this reason, most scientists, I think, are now comfortable with the idea of popularizing science. Since nearly all support for science comes from the public coffers, it would be an odd flirtation with suicide for scientists to oppose competent popularization. What the public understands and appreciates, it is more likely to support. I don't mean writing articles for Scientific American, say, that are read by science enthusiasts and scientists in other fields. I'm not just talking about teaching introductory courses for undergraduates. I'm talking about efforts to communicate the substance and approach of science in newspapers, magazines, on radio and television, in lectures for the general public, and in elementary, middle, and high school textbooks. Of course, there are judgment calls to be made in popularizing. It's important neither to mystify nor to patronize. In attempting to prod public interest, scientists have on occasion gone too far. For example, in drawing unjustified religious conclusions. Astronomer George Smoot described his discovery of small irregularities in the radio radiation left over from the Big Bang as seeing God face to face. Physics Nobel laureate Leon Lederman described the Higgs boson, a hypothetical building block of matter, as the God particle, and so titled a book. In my opinion, they're all God particles. If the Higgs boson doesn't exist, is the God hypothesis disproved? Physicist Frank Tipler proposes that computers in the remote future will prove the existence of God and work our bodily resurrection. Periodicals and television can strike sparks as they give us a glimpse of science, and this is very important. But, apart from apprenticeship or well-structured classes and seminars, the best way to popularize science is through textbooks, popular books, CD-ROMs, and laserdiscs. You can mull things over, go at your own pace, revisit the hard parts, compare texts, dig deep. It has to be done right, though, and in the schools especially, it generally isn't. There, as the philosopher John Passmore comments, science is often presented. Quote, as a matter of learning principles and applying them by routine procedures. It is learned from textbooks, not by reading the works of great scientists or even the day-to-day contributions to the scientific literature. The beginning scientist, unlike the beginning humanist, does not have an immediate contact with genius. Indeed, school courses can attract quite the wrong sort of person into science, unimaginative boys and girls who like routine. End quote. I hold that popularization of science is successful if, at first, it does no more than spark the sense of wonder. To do that, it is sufficient to provide a glimpse of the findings of science without thoroughly explaining how those findings were achieved. It is easier to portray the destination than the journey. But where possible, popularizers should try to chronicle some of the mistakes, false starts, dead ends, and apparently hopeless confusion along the way. At least every now and then, we should provide the evidence and let the reader draw his or her own conclusion. This converts obedient assimilation of new knowledge into personal discovery. When you make the finding yourself, even if you're the last person on earth to see the light, you never forget it. As a youngster, I was inspired by the popular science books and articles of Gamow. I'm getting hung up on this guy's name. George Gamow, James Jeans, Arthur Eddington, J.B.S. Haldane, Julian Huxley, Rachel Carson, and Arthur C. Clarke. All of them trained in, and most of them leading practitioners of, science. The popularity of well-written, well-explained, deeply imaginative books on science that touch our hearts as well as our minds seems greater in the last 20 years than ever before, and the number and disciplinary diversity of scientists writing these books is likewise unprecedented. Among the best contemporary science popularizers, I think of Stephen Jay Gould, E.O. Wilson, Lewis Thomas, and Richard Dawkins in biology, Steven Weinberg, Alan Lightman, and Kip Thorne in physics, Roald Hoffman in chemistry, and the early works of Fred Hoyle in astronomy. Isaac Asimov wrote capably on everything, and while requiring calculus, the most consistently exciting, provocative, and inspiring science popularization of the last few decades seems to me to be Volume 1 of Richard Feynman's introductory lectures on physics. Nevertheless, current efforts are clearly nowhere near commensurate with the public good. And of course, if we can't read, we can't benefit from such works, no matter how inspiring they are. I want us to rescue Mr. Buckley and the millions like him. I also want us to stop turning out leaden, incurious, uncritical, and unimaginative high school seniors. Our species needs and deserves a citizenry with minds wide awake and a basic understanding of how the world works. Science, I maintain, is an absolutely essential tool for any society with a hope of surviving well into the next century with its fundamental values intact. Not just science as engaged in by its practitioners, but science understood and embraced by the entire human community. And if the scientists will not bring this about, who will? And that is the end of the chapter. Just thinking about whether or not I want to read another one. Well, the next chapter is chapter 20. It's called House on Fire. And he co-wrote this with someone named Andrew Yan. I think he mentioned her earlier in the book. Well, I think I'm going to take a break. Maybe I'll come back to it later and read that chapter 20. All right. See you later.